So I'll begin with a brief introduction about all of G-2, and then I'll spend most of the time talking about the hadronic vacuum polarization contribution, mostly from the lattice, but I'll also talk a little bit about the data-driven results. And if there's time in the end, I'll talk about the hadronic light-by-light contribution and then end with a summary. So just to get definitions straight, I think you all know that spin 1/2 particle has a magnetic moment, and it's proportional to a G factor. And the thing that experimentalists measure and the thing that we calculate is this so-called anomaly, A mu, which is just that G factor minus 2 divided by 2. So I always like to start with the experiments because I'm completely in awe and amazed by what they've done. Most of you probably know that the modern storage ring experiments for measuring the anomalous magnetic moment started in CERN from the late 50s to almost 1980, and they ended up with a precision that was about 7 parts per million. And then the experiment moved across the Atlantic to Brookhaven, and at the end of the last century, just the beginning of this century, they got down to 0.54 parts per million, more than an order of magnitude improvement. And now at Fermilab, the experiment at Brookhaven was literally moved to Fermilab, and they've been running for a while now. They started with one run. They've now done 6 runs. They started with 0.46 parts per million, and they ultimately want to get down to about 0.1, maybe a little bit more per million. There's also an experiment planned at J-Park in Japan, which is it's being built right now, and they probably won't take data for quite some time. So let me now turn to the theory and give you a brief summary of where the theory stands. Of course, by far the dominant contribution comes from QED, starting with the Schwinger term, and this is the result. If you add in the effects of the weak interaction to 2 loops, you get this contribution. It's also very precise. And then you got the hadronic contribution, so the hadronic vacuum polarization and the hadronic light-by-light contribution. And the important thing about these 2 contributions is that their uncertainty dominates the error budget for the anomalous magnetic moment. And so we're working very hard, both on the lattice and off the lattice, to calculate these 2 contributions. So mostly I will talk about this contribution, and in the end I'll talk about this contribution. So the light-by-light is down considerably in magnitude from the HVP, but the error is comparable. So we have to handle both. So there's a worldwide group of theorists and even some experimentalists working on this problem. It's called the muon G-2 theory initiative. In fact, they just had their annual plenary meeting in Bern last week. And this is basically a summary from the 2020 white paper. It was actually updated during the snowmass process a year ago, but it didn't really change. And if you take this value from 2020 theory for the standard model and compare it to the experiment, that basically includes the Brookhaven experiment and the first run at Fermilab, then you find a 4.2 standard deviation discrepancy between theory and experiment. That doesn't include the lattice, except for the light-by-light contribution, which doesn't make a big difference here. And if we include the lattice, we'll see things change, look a little bit different. So Most of you also probably know that maybe less than a month ago, or about 1 month ago, Fermilab announced new results from runs 2 and 3, and they're really quite spectacular. They're now the total uncertainty just from the Fermilab experiment, which is this one, these two, run 1 and runs 2 and 3, and then combined run 1 through run 3, is now about 0.2 parts per million or 200 parts per billion. And they have another half of the data to come, runs 4, 5, and 6. And so they have a very good chance of meeting their precision goals, which is, like I said, is around 0.1 per million or 100 per billion. So if you take that new number for experiment, and if you add Brookhaven, you can see you even get a little bit below 0.2 per million. And you compare that to that theory initiative white paper, then what was 4.2 sigma becomes 5.1 sigma if you compare to the world average. Now, I said that was without considering the lattice data, and again, most of you know that the BMW collaboration has done a wonderful calculation already in 2020 with sub% errors, and if you use that value, then you're only discrepant with the experiment by a bit less than 2 sigma. So the whole object now is to improve errors, both on the lattice side and the data-driven side, and again, come to a consensus value for the standard model and compare to experiment, hopefully in another couple of years by the time the experiment announces their final result at Fermilab. Okay, so now let me dive into the vacuum polarization contribution. And before I get to the lattice, let me just say a few words about the data-driven calculation so you have an idea of what we're comparing with. So what we want to do is calculate this contribution. So there's a one-loop QED integral, and then there's a hadronic blob. Basically all possible hadronic states that can propagate between 2 vector currents. And the blob is, of course, hard to calculate. So for a long time, before the lattice came along, this was done by going to data. For E plus E minus goes to hadrons. So the vacuum polarization part you can get from a dispersion relation. If you know the experimental cross-section, you use the optical theorem to get the imaginary part. You stick that into the dispersion relation, and you get this hadronic contribution. You stick it into this one-loop QED integral, and you get the result for the contribution to the anomaly. And this is basically what that data looks like, the cross-section versus center of mass energy in the time-like region. And it's dominated by this region below 1 GeV, basically dominated by the 2 pion state. In any case, if you add up all these contributions and you stick it into that dispersive integral, you get something that looks like this. So you have the cross-section as a function of the center of mass energy squared, and you have some kernel function that comes from the one-loop QED diagram, and you integrate that, and you get the contribution to A mu. So that's what we mean when we talk about the data-driven result for the hadronic vacuum polarization contribution. And now let me turn to the lattice data. So I'll give you the sort of the punchline, the overall punchline first, and then we'll go into the details. So this is a summary that I could have told you, a couple of years ago for the total contribution calculated on the lattice compared to experiment and compared to data-driven results. So here's the BMW result, and I said it had sub% errors, so this is what it is. If you take the white paper lattice average, which actually was done before BMW's result was published, so their result didn't appear in the white paper average, you get this number, which is a little bit higher with a much bigger error. And here's the data-driven result again, with, again, sub% errors. So if you compare lattice average to data-driven, they're basically consistent with a large error. And if you compare BMW to data-driven, they're different by about 2 standard deviations. So they're not really that different. But the big difference is that if you use one to compare to the experiment, you get a 4 or 5 sigma deviation. And if you use BMW, you get less than 2. So they sort of sit in, BMW sort of sits in the middle. Okay, so that's the summary. And like I said, if you just looked at this, you might say, well, not much has changed in the last few years, but I'll show you that, in fact, a lot has changed on the lattice side, and even more change is coming very soon. So let's see what that means. Okay, so let me give you a brief rundown of how we actually calculate this on the lattice. So on the lattice, of course, we're interested in quarks and gluons and not hadrons per se. So we want to calculate these diagrams now where the quark or the blob you should think of as a quark anti-quark pair, and all possible intermediate states by dressing these quark and anti-quark propagators with all possible gluons. And there's a so-called quark-connected contribution where there's one quark to here and then back again. There's a quark-disconnected contribution. So the quark loops are only connected by gluons. And there's isospin breaking corrections that we have to calculate if we want to compare to the data-driven result. Okay? By far, the largest contribution comes from this guy. And so mostly we're going to concentrate on this guy, but I'll tell you a little bit about these. Okay, so the way we calculate this is quite simple. The blob here is just this 2-point electromagnetic correlation function, which we calculate in Euclidean spacetime. So here's the electromagnetic current. You have one of these for each type of quark you're interested in. So up, down, strange, bottom, and charm could propagate in here. And you Fourier transform that, and you get a vacuum polarization function that basically from Lorentz symmetry and gauge symmetry has 2 terms, and they both have the same coefficient, which we call the vacuum polarization. And again, you stick this vacuum polarization into basically this one-loop diagram, and you integrate over all q squared, where q squared is the space-like momentum running around in this loop, and you get the contribution to A mu. Okay, so it looks very similar to the data-driven approach, except we calculate everything directly in Euclidean space, or in the space-like region. And this kernel F here, again, is a known kernel that just comes from the one-loop diagram. There are various ways to put this current on the lattice, a so-called local current, where it's defined at one site, or a conserved current, where it's defined over neighboring sites. They have different lattice spacing corrections, but in the continuum limit, they have to give the same answer. Okay, that's the way we did the calculation originally. Now it's become conventional to do it slightly differently in something called the time momentum representation, where we interchange the Fourier transform and the integral over momentum space. And the central object here is, again, the correlation function calculated on the lattice, but in Euclidean time, where we just calculate the 2-point correlation function as a function of separation in Euclidean time of our 2 currents. And again, we can define a kernel based on the one-loop QED integral, and we put those 2 things together, the correlation function, and this kernel, and we simply sum over all time slices over the lattice and get the total contribution, just like we did before. Except now instead of integrating over momenta, we integrate or sum over Euclidean time. One of the nice features about this setup is the so-called double subtraction. So this term here basically cancels the divergent part of the vacuum polarization, which we have to do, configuration by configuration. So we don't have to calculate that, say in an average, and then subtract it. And then this one here takes care of the leading finite volume contribution. So that's the so-called double subtraction and makes this method effective. Okay, so what does that look like? This is sort of a canonical picture of the lattice data, the blue crosses. And this is the integrand. So again, if you just summed up everything under the curves, you'd get the total contribution. You see that, and I'm comparing that the purple line here is from the data-driven side, so from the R ratio or the cross-section for E plus E minus goes to hadrons. And you can see this lattice calculation here is only for one lattice spacing, one volume, and so on. But they already agree quite well. They do differ, if you look carefully, they differ at very small t, which is not surprising, so there's lattice discretization effects. And then as you go to long distance, the lattice data becomes noisy because this tail is dominated by 2 pion state, which is hard to calculate. And of course, what you want to do is do this calculation many times, different lattice spacings with different volumes, and extrapolate to the continuum and infinite volume limits. And those are the two biggest systematic errors in the calculation. Okay, so now let me talk about the calculation in a little bit more detail and talk about this idea of windows, which is the way the community has decided to attack the problem. So the idea of the windows is to break up that calculation in terms of short distance, intermediate distance, and long distance. And the reason being is that we can actually do a pretty good job already if you think about the systematic errors for the intermediate distance. We can also do a pretty good job already for the short distance if we're careful, but it's the long distance part that's the most difficult. So the idea of the lattice community coming out of the white paper and after the BMW result was to take it step by step, see that we could get agreement on the intermediate window first, then the short distance window, and then we move on to the long distance window. So now I'll concentrate on the intermediate distance window and then tell you a little bit about the short distance window and the long distance window and where we're going. So the window is easy. You just, instead of the sum I just showed you, you stick in the same stuff, but you also add in this, basically you can think of it as a smooth step function or filter to project out the various contributions. And so, and you can do the exact same thing with the data-driven side, with the R ratio data. So you can do a direct comparison between R ratio and the lattice for each of these windows and see where the discrepancy might be arising between lattice and E plus E minus goes to hadrons. Okay. So this is what the windows look like in Euclidean spacetime. So this is the short distance filter, this is the intermediate distance filter, and this is the long distance filter. And this is what they look like in the time-like region in energy space. So they take, they spread out in the energy space. And this is what so these are the windows. This is what it actually looks like for the contribution to the correlation function. Times this kernel. So this is the integrand again. This is the full integrand. This is the short distance contribution. And this is the long distance contribution. And again, this is what they look like in energy space. So this is a summary of the window results. This is basically a year old since all of these lattice calculations have been done. And the striking thing here is that there's essentially 8 different lattice calculations, and they're all consistent to very high precision for this intermediate window quantity. This is from Martin Golterman's talk at the lattice meeting, and they have a way of extracting it. So this is just the up and down connected quark contribution only. So these are the lattice results, and you can see they're very, very consistent, very precise. This is what you would get from the data-driven result for that same quantity. And if you average these and compare to this, they're about 6 standard deviations different. And in magnitude, this is about half the difference between the full data-driven result and the BMW result. So really already half of the difference comes from this intermediate window quantity. And the lattice is quite in agreement that this is the value and not this, okay? If you add in all the other contributions from all the other quarks, the isospin breaking and so on, then you get this result on the lattice on the right, and you get this. These are different data-driven determinations. But you see they're still discrepant. So again, mostly it's in the light quark connected contribution. Okay, what about the short distance window? So a few groups now have calculated the short distance window. This is a summary slide from Simon Kuberski's talk at the lattice meeting a couple months ago. And you can see again that the lattice is in very good agreement. And again, this is just the up and down connected only part. You see it's much smaller contribution of the total. And in fact, in the ETMC collaboration has compared it to the R ratio result, and you see that they're in agreement within errors. So there's not a discrepancy between lattice and data-driven for the short distance window. Okay, what about the long distance window? How am I doing on time? 17. Okay, good. So the long distance contribution, like I said, is much more difficult because of the long range QCD physics that we're talking about. It's statistically very challenging. And we basically have 3 methods by now to handle that long distance contribution that go way beyond just doing the calculation more times on more configurations. And so the first of those is called a full volume low mode average, where we calculate the contribution to the correlation function from the lowest n eigenmodes of the Dirac operator, which we know from every point on the lattice to every other point on the lattice. So if you like, we do a volume average on the source and a volume average on the sink. And that improves your statistics on each configuration dramatically. And because the low mode, because the 2-pion state dominates the long distance tail, those low modes actually saturate most of the contribution. So it's very effective in handling that, at least part of the long distance contribution. And these are just 2 examples of that, how things improve when you do a low mode average. So these are staggered fermions, so they oscillate from time slice to time slice. But if you just look at the blue points, this is without the low mode average. And the black points are only the low mode average, so you already see that the statistical errors are much, much smaller. And then if you include the low mode with the non-low mode part, which gives you the high mode parts, you get the red points, which have error bars that are almost invisible compared to the blue ones. So a huge improvement. And this is also an example from the Mainz collaboration. So just compare the blue circles where you can maybe not even see the error bars to the black points where you see the error bars. So that's the first thing. The next step is something called we call the reconstruction of the long distance tail by doing essentially an exclusive mode calculation where, again, we use a variational or GEVP method to calculate the n first states in the correlation function. So Lorenzo gave a very nice explanation of the GEVP yesterday, so I won't repeat that, but it's exactly the same thing that we're doing here, but for the vector two-point function and not for the nucleon case that he's looking for. So here's an example from Mainz, and they show the contribution to the correlation function from the lowest 2-pion state, and then they add in the second one and third and fourth, and you see, so the black points are the total, just the vector-vector correlation function. They quickly saturate, and especially for the low mode part, you see they saturate very quickly, and they're much more precise. It's much more precise way of doing the long distance part of the calculation. So that's the second improvement of calculating the long distance tail. And then finally, there's something called the bounding method, where we define upper and lower bounds for the correlation function. And you can see that these bounds overlap at some point, usually at some point, at some distance that's much shorter than the ultimate distance that you want to go to. And so you can get an improved estimator for the correlation function by looking at the place in the region where the two bounds first overlap, because they're at shorter distance and therefore less noisy. And there's an improved bounding method that has to do with this reconstructed tail that I mentioned, but I won't go into the details. So those three things allow us to do a calculation of the long distance part with some precision. Now, just quickly, there's some updates. These are all things that were talked about at the Lattice meeting, and you can click on links to go to those talks at the Lattice meeting, so I won't spend a lot of time on these. I want to spend some time on very preliminary but recent results by the RBC collaboration. So let me talk about our long distance contribution, which I think has a chance of being the next calculation from the lattice with sub-percent, even maybe 0.5% error on the total contribution. So we're using domain wall fermions. These are the ensembles that we're using, the pion masses and the lattice spacings for the calculation that I'm about to describe. It's really this point and this point which have about the same volume, but different lattice spacings, and then this point which has a slightly larger volume and slightly smaller lattice spacing. These other ensembles are in production, and we'll use these to estimate finite volume errors at this coarser lattice spacing. And these are all at physical pion mass. Okay, so here's the first thing. We'll talk about the spectral reconstruction of the correlator at long distances. So just like Lorenzo talked about yesterday, we do a GEVP analysis. In this case, this is the finest lattice. We have the 8 lowest states in the correlation function. Okay, these are mostly 2-pion states. And you can see that they're determined very precisely. So there is some residual excited state contamination, just like Lorenzo explained. We can get rid of that excited state contamination by fitting this to an exponential plus a constant. And that's what we do to get the energies. And at the same time, when you do the GEVP, you get the eigenvectors of the GEVP, which tell you how to make these, how to project the operators onto states of, onto each individual state. And these are the coefficients that you need. These come from the GEVP. So the lowest state is predominantly part of the vector-vector correlation function. In this case, it's a smeared operator, but it's the vector-vector correlator. And then one of the lowest 2 pion state. Okay, and then the rest of these are higher momentum pion states, and they don't contribute very much for this lowest energy state. If you go to higher energies, things change a little bit, but not so interesting. So if you take those coefficients or eigenvectors from the GVP, you can reconstruct the overlap with the vector current between each of these individual states. And from these overlaps and the energies, you simply reconstruct the correlation function for those 8 states. And, whoops. If you do that, this is what you get. This is just one state. And so what I'm comparing here is the reconstructed correlator from those states divided by the total correlation function. So, things should asymptote to 1 here. At short distance, of course, the low energy states don't saturate the correlator, but at long distance, they saturate the correlator, and you should see this ratio go to 1. And that's just what you see. So here's the lowest energy state, then 2 states, 3 states, 4, 5, and then they saturate. And the errors here that get large at long distance, those are coming from the denominator, not from the numerator. And what we're really interested in is the numerator. The numerator is blinded, so we don't really know what the absolute value of the correlator is until the very end when we unblind to get the result, because we don't want to bias ourselves. But this ratio, the blinding factor is the same, so the ratio, the blinding factor cancels out. So that's the finest lattice spacing. That was done by one group out of 5 in our collaboration that are doing the analysis. And each group has a different blinding, and they're sort of separated. And in the end, we'll do relative unblindings between the groups. And then at the very end, we'll do a global unblinding. There's actually another group that started doing the analysis. So this compares that ratio between 2 of the groups, and you see that they compare very, very well. So the analysis is ongoing, and I think, certainly by the end of the year, we hope to have this result out. Okay, this is what the integram looks like from the reconstruction part compared to the total. So again, you see the errors are much, much smaller at long distance for the reconstructed version. And if you add them all up, for 4 states or 5 states, this is what you get. Depending on where so what you do is you add up at shorter distances, you use the full correlation function where it's accurate. At longer distances, you switch over to the reconstructed correlator where it's more accurate. And this just shows the result as a function of that time where you switch over between one and the other. And you can see it's quite robust. It doesn't really matter within some region where you do the switchover point. And by the way, this is for the long distance window only. And this is blinded. So the blinding factors can be anywhere between 0 and 4. And they're randomly assigned, so we don't know what they are. So this sort of accidentally comes out close to the total contribution, but it has nothing to do with just the total contribution. It's just the long distance contribution. Whoops, went the wrong way again. Okay, that was for one lattice spacing. Now, if you do it for the 3 different lattice spacings, you get these points. And again, just the long distance contribution blinded. We can do finite volume corrections and slight mass retuning corrections and so on to get to the physical point and infinite volume, and then you get these 3 points here. Okay? So then you just need to extrapolate those points to the continuum limit. And this is what it looks like. Doing the calculations slightly different ways. Like I said, there are different definitions of the currents. They have different finite lattice spacing effects, but in the continuum limit they should agree, and they agree. So this is just a simple linear fits in A squared. Reiner will probably ask me about that. Oops. Okay, so, and these are the results that you get. Again, still blinded. There are different ways of setting the scale, setting the physical quark masses. One we call the BMW world, because BMW defined it one way, and one we call the RBC UKQCD world, because we defined it that way. And they differ by about 1 standard deviation, but they're actually very consistent. And if you add up all the errors, just for the long distance part, you get this, again, for the blinded value. And if you assume that the R ratio is correct, which is unblinded, we can calculate the long distance contribution from the unblinded R ratio data. That would correspond to about an error of 3.5 times 10 to the minus 10, which, if you compare to experiment, experiment is down around, I think experiment now is down around 2. Or it might be close to this. Anyway, they're close. So this is about halfway to our goal. We want to reach the same precision ultimately as the experiment, or 0.1 to 1 to 2 parts per mil at the end, and we're on our way. I think this actually looks pretty promising. Okay. I should get extra time because I've taken about 5 minutes trying to click between slides. Okay, so how do we finish the whole thing? So what I told you was basically isospin limit for the up and down quark contributions. We want to improve our disconnected quark contribution, which is actually very small compared to the connected. Improve our strange quark contribution, redo the charm quark contribution. Bottom is pretty negligible. And we should have, our goal is to have a sub 0.5% for absolutely everything, let's say by the middle of next year, or sometime next year. I hope it's by the middle of next year when Shoji and company host the next muon G-2 theory initiative meeting at KK. But we'll see how it goes. I mean, once we get the long distance part done, then the rest of this stuff should come quickly. Okay, so that's the status. I won't have time to do anything else, including change the... So the other contributions are in good shape. Let me just do this. This is from the white paper, strange and charm contributions, lattice. Everybody agrees they contribute little, so it's not really a problem. These things will improve a little bit, but already they're almost at the precision we need ultimately. Disconnected, we need to improve a little bit, do a little bit better job, but again, that's happening by many collaborations, and that will happen. And you can see it's a small contribution with the opposite sign as the connected. Isospin also is a little bit messy right now. BMW's done a complete calculation of all the contributions, and other groups have done some of the contributions, but not all. And again, that will change in the next year or so. Mainz has already showed some new results at the Lattice meeting. And there was the only published result since the white paper and BMW for the total contribution came from Abend et al. But the precision is is still too big to, it's still consistent with both the lattice average and data-driven, so more work needs to be done from that group. This is the summary. 0 minutes, so I guess I can stop here. The important thing to notice here is that lattice spacing determination is becoming a dominant error in the whole business, even more than statistical errors and other systematic errors. And so if you want to be in this game where we get down to 1 per mil for the total error, then the lattice spacing error, we have to know the lattice spacing to 1 per mil. And people are getting down to that. Okay, so I'll stop there. The light by light's in good shape, don't worry. Let me just leave my summary up there. Thank you.